Welcome back to the 5G Hack Them All summer course here at Aalto University. Next up, Edward Oughton from Oxford University. Thank you.
Good afternoon, good morning, wherever you are. My name is Edward Oughton, and today I'm going to be talking to you about the 5G assessment work that I've been carrying out recently. So just bear with me 1 second. I'm just going to share my screen so that you can see the presentation. Is everyone able to see the screen okay? Please let me know if you are unable to see. Great. Okay, so in this presentation, I'm going to do 3 things. I'm going to give you a bit of context about 5G generally across the industry right now. And then I'm going to talk to you a bit about some of the background projects which we've done, which have got us to this point. And then finally, I'm going to present the global 5G assessment that we're currently working on. Some of the results are still preliminary. But this work is going to be surfacing in the next couple of months, so I'm excited to share with you today what we've been doing. So what's the current industry context for 5G deployment? To be honest, it's pretty challenging. So what I'm presenting here are metrics of revenue across OECD countries. So we have the earning before interest, tax, depreciation, and amortization on the left, and we have the post-tax return on capital employed on the right. And what I'm trying to emphasize here is that generally there's a downward trend in revenue. So it's a bit of a mixed bag here on the left, but then on the right you can clearly see that revenue is decreasing. And actually this is really challenging, therefore, to deploy what can be quite expensive technologies. If you actually look globally, average revenue per user, so that's the amount that you pay, has essentially been decreasing across all countries as well. So this is from the GSMA, so it's the Cellular Operators Industry Association. And last year, the average revenue dropped by about 1% globally across all countries. So that includes low and middle income countries. So this is tough. And the reason why it's tough is because mobile traffic is increasing at a very rapid rate. So whichever forecast you want to take, whether it's Ericsson or Cisco, data traffic is increasing rapidly, and operators need to meet that traffic demand. And it's essentially being driven predominantly by video. So you can see here the composition of the traffic, and video is by far the largest component, and it's increasing at a very rapid rate as well. And that's because, we all have smartphones. We want to access video on demand wherever we are, and that's really driving traffic. So the problem, therefore, both for operators and also governments who may want to improve coverage and capacity of new technologies such as 5G is, well, which strategies actually are sensible? Which strategies perform well? They balance rolling out capacity and coverage with the cost, given the fact that there's only a certain amount of revenue that can be generated from users, and overall that's generally decreasing over time. So essentially, there are 3 ways to enhance a wireless network. I'm sure many of you have been through this already on the course, but essentially you can increase the spectral efficiency of the technology. So for example, move from 3G or 4G to 5G, so fit more bits per hertz on a radio wave. But that's technically challenging because of the Shannon bound. You can add more spectrum to your network, but spectrum's generally quite scarce, particularly if it's the kind of desirable sub 1 gigahertz spectrum that people want because of the good propagation characteristics. So that can be hard to obtain. And then as a last resort, you can always build more cells, but that's actually quite expensive to add sites. And this is one reason why we have poor rural coverage problems. Because operators generally make money off only a small portion of their sites, maybe 30 or 40%, for example, in the UK, and then the rest they don't actually make that much revenue from. So obviously there's a social need for us to have that, and that's why we have regulatory decisions to push out coverage to underserved areas. So how did we start doing this work? Well, the UK government committed to trying to roll out 5G relatively quickly back in 2015, 2016, and that was driven by the fact that we have really bad 4G coverage in certain places. You know, it can be bad in central urban areas, but it can also be bad in some of the remote northern and western areas. So this became a hot political topic, and it just happened that we were doing some infrastructure modeling work at the time on this area, and we were able to basically produce evidence that fed into the UK's 5G strategy for deployment. And actually, this work became a telecommunications policy paper, which you're able to go and have a look at, which is available open source on the Telpol website. It's linked here. But actually, we had quite a large influence on the report. So, for example, we calculated the investment cost to get to 100% population coverage. And that directed their focus at first for 5G to deploy predominantly in urban suburban areas. We also calculated the cost of deploying 5G on areas of the transport network which are currently poorly served by existing mobile technologies, so predominantly on the rail network and the road network. And also, we advocated for universal service obligation or some sort of regulatory mechanism which may help to try and fix the coverage gaps that we currently are experiencing. This has now turned into a shared mobile network, a shared rural mobile network, which basically is a collaboration between the operators. A lot more, it's more similar to the Scandinavian model for deploying in rural areas. But it was good to have this sort of impact on the strategy, especially as it kind of set the groundwork for some of the analytics that we started to produce. And we produced a series of papers off the back of this work, essentially, and I'm not going to go through each of them specifically, but one focused very much on the rollout of infrastructure over time to different places based on the strategy, whether you're integrating new spectrum or deploying small cells or using a combination of these two approaches. And that led essentially to an analysis which we carried out for the Dutch government, looking at 5G deployment, again, under different types of scenarios. And this time we started to focus on the cost per user, which is really important. So generally, as you move from urban areas through to rural areas, obviously the costs start to increase. And you need to balance that against the demand and the revenue that may be available in certain places. More recently, we've been doing some open source assessment work, and we've started to release our code base, which you're able to go and access. So we published a 5G simulation model in the IEEE Access journal last year now. And actually, you can go onto my GitHub profile if you would like, for anyone who's doing either kind of engineering work or data science kind of work, and look at the different software repositories that we have there. So I just showed you the Python simulator for integrated modeling of 5G. That's a pretty interesting one. It allows you to do the engineering and the economics in a single framework, which reduces certain uncertainty. We've got some Python implementations here of classic propagation models. So the Longley-Rice irregular terrain model is it's an old model. It's been around for about 40 years, but it's used by many people in industry. And we wrote a Python version of that model, kind of translating the old Fortran 88 code. And I think I'm just about to show you some details on the 4-dimensional network planning work that we've been doing, which is kind of experimental at the moment. But you can go and have a look at some of these repos if you would like. But I noticed on the course details that you were having some focus on autonomous vehicles, connected vehicles, and a lot of the network planning and assessment work that we do often just tries to estimate a capacity at a single point in space, at a single point in time. And really, we're trying to push that forward now to do more kind of spatio-temporal analysis of the demand that's been placed on cellular networks so that we can do the kind of quality of service analysis that would be interesting for connected vehicles. So what we actually did was we took a transport model for the whole of the UK road network. And essentially, we've been estimating the flows on main transport routes through the day at an hourly basis, and then estimating the demand that it's able to place on the surrounding cellular networks. You can see the blue dots here. And this is for Central Oxford. And this is just a small demo, which we've been doing at the moment. It was actually funded by some experimental work, some experimental funds that we got from Facebook Research. But this is kind of where our work is wanting to go in the future, to do more kind of real-time simulation of different potential capacity demands in the network. So that's general background of kind of where we've come from and where we're going to go now. So I'm going to give you a bit of an overview of the global 5G assessment work. I should say that this work is funded by the World Bank, and the aim is to look at how 5G deployment may take place in low and middle income countries. And essentially we have three main research questions. So number one, we're interested in the extent to which different technology decisions affect the viability of 5G rollout. And I'll explain what I mean by technology decisions later in the presentation. The research question number two was how do different business model options affect the viability of 5G rollout? And I'll be specifically focusing on infrastructure sharing, different types of infrastructure sharing in this particular instance. And for research question three, what are the impacts of different policy and regulatory options on the rollout of 5G in terms of the capacity, coverage, and cost of different infrastructure strategies? And the aim within this approach essentially is not necessarily to model a specific mobile network operator, because that can be commercially sensitive. We may not have the data either to model a specific operator and say something specific about one of the market players. So we adopt this approach, which is taken within many of the regulatory models, the open source regulatory models used by different government agencies, which focuses on modeling a hypothetical network operator. And basically this operator has an average spectrum portfolio. It has an average number of sites, so an average quantity of sunk costs in existing infrastructure, and therefore the aim is to emphasize that we're able to estimate some sort of average incremental cost to a player within a market which we're modeling. So the analysis focuses on an approach which uses scenarios. So scenario analysis is a pretty standard technique which is used widely by modelers in a variety of circumstances. So often scenario analysis is used when you might have limited scientific information that allows you to specifically model the exact scenario that you want. So you're able to, say, develop a model with a set of assumptions, and then you're able to ask what-if questions and see how the model responds under those different conditions that you might stress the tool against. And I sketched out those three research questions, and really here I'm now starting to state exactly what we mean by them. So in terms of technology, the question is, well, many operators, particularly if you're, for example, in sub-Saharan Africa, they might be focusing right now on 3G and then focusing on deploying 4G. So 5G is really not necessarily on the radar yet. And therefore the question is, well, should I go and deploy 4G, or should I skip and try and leapfrog straight to 5G? This is a question many operators are currently being faced with, so we try to produce some analytics here. The backhaul component is really important because it's a larger cost factor in rural and remote areas, and they're the ones where perhaps you've got poor coverage. So we want to understand what the cost implications are for deploying either a fiber or a microwave backhaul. And then we want to test different business model options. So that's associated with infrastructure sharing. So in the baseline case, an operator builds its own infrastructure, its own dedicated network. But then in the passive infrastructure sharing circumstance, then an operator would share the non-electronic components with another operator to reduce cost. And then in the active infrastructure sharing circumstance, an operator might share all of the infrastructure. So it's a single multi-operator radio access network that includes sharing radio heads, baseband units, all electrical components. And then finally, focusing on the policy options, and we are refining these as literally as we speak in the piece of analysis which we're working on. We are including the ramifications of changing spectrum costs, the ramifications of applying subsidies to different parts of the system, either on the demand side, so where consumers pay for services, or on the supply side, where operators deploy infrastructure, and also changing general taxation rates. So these are the different options that we want to test within the framework which we're developing. So in order to approach these questions, we need a model which is actually able to assess the costs of upgrading the radio access network, the backhaul component through to any type of aggregation or metro network that it may be attached to, and then eventually to a core network. So we need some sort of general architecture model. And I mentioned before that backhaul is going to be increasingly important. So essentially, the portion, so the connection which connects a site tower, which has a set of radio heads and antenna, that's essentially the backhaul. So it's the connection which links the site back into another network asset or the general internet. The type of backhaul options available to us essentially are fixed fiber, a microwave or wireless link, or using satellite. And they each have their own particular niches. So fiber is very economical in large, dense urban areas where traffic density is high, but it's less economical in smaller settlement sizes when you've got fewer users. Microwave currently in many of the countries which I'm going to be modeling has by far the largest share in terms of the backhaul technology, and satellite is actually, it's getting better. It's always getting better. It is quite expensive to shift large amounts of data, and it's usually deployed in the most remote situations. Maybe only between about 3 to 5% of the sites in many of the countries that we've been working on actually use a satellite link. So 5G. I'm sure you have had other talks on many of the fancy 5G features, which include network function virtualization, software-defined networks, introducing compute at the edge of the network to reduce latency, so mobile edge computing, the ability to deliver specific network slices, so the ability to give quality of service to certain consumer or industrial use cases. And also this move towards potentially centralized cloud radio access network, away from the kind of distributed model that maybe we've seen in previous generations. This is quite high level. I'll give you more specifics about what I mean by each of these as we move on. But I'm assuming that you have at least some general understanding of these key technologies. I think the real problem is that a lot of this is being worked out within the engineering literature right now. As someone like myself who's focusing on the kind of techno-economics, so it's how does the engineering then translate into the economics for the operators or for governments? This is very dynamic and changing, and there's really been very small amounts of work on what the cost implications of these different technologies are. So it's been quite arduous over the last 6 months to try and build models which are able to capture all of these features. There are different flavors of 5G. So I'm going to emphasize the fact that there is a standard 4G network architecture where you have the 4G radio interface and then the 4G evolved packet core, which data transfers across. Most of the 5G flavors which we're seeing deployed at the moment are non-standalone, which basically means that you have the new 5G new radio interface, which you're able to access, that might have new spectrum, might have higher spectral efficiency, it might have larger bandwidth, but it still goes across the 4G evolved packet core, and therefore there's no specific quality of service. Once it goes into the general internet, there may be latency implications associated with this type of 5G approach, although the general consumer will probably receive quite a considerable uplift in the capacity that they can access. And then kind of looking over the next decade as we move up to 2030, we're likely to see more standalone 5G deployed. And that's essentially where you have two separate networks for each of the different technologies. And basically the 5G component will go straight onto a 5G core network, which has its own quality of service standards. And this is more futuristic. It's probably going to be a lot more expensive. But this is essentially the kind of 5G nirvana vision that is being sketched out for where we might go over the next 10 years. So, well, how do we assess this? Essentially, the method has a variety of steps. So I'm going to talk about how I first cluster countries into groups, and then I do some demand estimation for the demand side, so how much traffic is going to be generated, how much revenue is going to be generated. And then I do some least cost network design to say, well, how do I meet that load with the least amount of capital invested? And then I'm able to do some assessment around what happens if you provide subsidies or you provide spectrum price reductions. So firstly, what I did for all of the low and middle income countries in the world was I took three main metrics which affect the demand side and supply side for 5G. So how much will people be able to pay on the demand side, and how much will it cost to deploy? And those three metrics were essentially the gross domestic product per capita. So this is a measure of wealth. Population density, obviously this is going to affect the network which you deploy, so the number of people per square kilometer. And then 4G coverage as an indicator of the existing level of access for cellular. And also it's a good indicator of the number of sunk costs which have been undertaken into sites and fiber and things like this, which affect ultimately how you deploy the network. And I developed 6 individual clusters within the low and middle income countries that we identify. And within each of those, we essentially select 8 countries that we're then going to model. The point of doing this clustering exercise is that then when we get cost estimates for each of the countries in these clusters, we're then better able to generalize those costs for deployment to other countries within the same cluster. So it's quite hard to model every single country in the world. That would be very, very time intensive. But we're able to more rigorously generalize the costs of analyzing a small number of countries to lots of other countries if we take kind of this approach where we group together countries which have similar cost factors. So we have these 6 clusters. Let's see if I can remember which countries fit into these. So we model in cluster 1, Uganda and Malawi. In cluster 2, Senegal and Kenya. In cluster 3, we have Pakistan. Cluster 4, we model Albania. Cluster 5, we model Peru. And in cluster 6, we model Mexico. And some countries were very kind and actually gave us cellular sites data for this analysis. And then in other countries, we had to make some estimates as to the number of cells which are already present in those locations. So I appreciate this is a big diagram, and I'm not going to spend too much time on it now, but I just want to show you that the method for doing this is split into 3 key modules. And if you look at the software code for PyTal, the Python Telecommunication Assessment Library, you can see that they're divided quite nicely into these 3 different areas. In essence, what happens is On the demand side, we estimate how much traffic there is, given how many people there are, the cell phone penetration, the number of smartphones, and that helps us understand what the demand is per square kilometre. And I'll talk more about this as we go through the method. And we also estimate what the revenue would potentially be based on the average revenue per user, the number of people in each local area. And then we take these metrics forward into the supply side, where we do some radio engineering modeling. So essentially, we take the spectrum portfolios that are present in a particular country. We make estimates for the number of sites, and then we're able to estimate how much additional capacity we would need to meet different capacity scenarios, and therefore how much additional infrastructure we might need. Either brownfield upgrades of existing sites or greenfield upgrades, which provides us with some understanding of the network cost for a particular option. And then we can take both the demand side revenue and the cost into the assessment module and then basically do some calculations. So we're able to say how much the spectrum would likely cost, how much tax the operator might pay, how much profit they might be able to gain, and how much state subsidy would be needed in areas where there isn't enough capital to deploy. And then we get a set of results out that we're able to do a variety of things with based on the capacity in local areas, the coverage by different technologies, and the cost. Okay, so how do we estimate the number of users in each local area? Well, I take the GSMA data between 2010 and 2020, and we can see for each of the countries in the different clusters here that the unique mobile subscribers in 2020 ranges from about 30% in Malawi up to about 78% in Albania. And then I forecast forward at about a 1% annual growth rate for each time step within the period which we're modeling. And I'm able to estimate the users using this. So I use a satellite population database. So this is global in scope. It allows us to extract the population for any area in the world, for any geometry that we provide. And we're able to relate it to the penetration rate, which we get from this graph, and the number of networks. So this is the market share for the number of operators. And that means that for the region I, so for an individual region, we're able to say how many users we think there would be for a particular hypothetical operator in each of these countries. And then we need to estimate the actual data demand. So how do we do this? Well, we take the users from the previous calculation, we take an estimate of the smartphone penetration, and then we take an estimate for the capacity that we want to give each user. And in the three scenarios, we basically give different capacities to different users in urban, suburban, and rural areas. So this is the number of megabits per second per person. So in scenario one, it's about 25 meg per person in an urban area and about 2 meg per person in rural, going all the way up to some very, very high capacities, which are, for example, in scenario 3, 400 meg in urban and about 10 meg per user in rural. And we're able to use these stats along with some understanding of the number of users who use the network at once. So this is called the overbooking factor in cellular network dimensioning terms. And that gives us some traffic demand for a local area. And that's one of the key demand side calculations. Revenue estimation. So how do we do that? Well, we take the GSMA average revenue per user for each of the countries that we're modeling. And we treat the average revenue as the data point that they state. And then we also provide a low average revenue per user and a high average revenue per user. And we're able to get the revenue that an area can generate over the study period, which is 10 years, for the number of users. And we basically take the net present value. So this is just a way in business modeling to account for the fact that money value changes over time. So we're trying to get the total amount of revenue that can be generated across the 10-year period, but we just want to know how much value there is for that amount in a single year. And that's essentially what we do. So I'm showing you here Peru, and what I'm trying to emphasize is that I actually use the nightlight luminosity to estimate how much each user is likely to pay. So if I just show you, I hope you can all see this. Here's an example from Mexico. And essentially what I've done is from the satellite layer, I've taken the amount of nightlight luminosity. So if you consume electricity, you emit light at night, and that could be from street lights or from your house. And it turns out that this amount of nighttime luminosity is highly correlated with your socioeconomic status. And that's highly correlated with obviously how much you earn, how much you could pay for a cellular subscription. And therefore, I use this as a way to create consumption tiers for cellular users. And as this is global in scope, I can do it for any country. And my model essentially just cuts from the national data set and allows us to then start understanding spatially how much people might pay for different services in different places. Okay, moving on. So this is about global assessment, and I'm sure there's lots of other people talking about the engineering aspects. So I don't want to get too much into the engineering methodology here. If you want to get into that, you can look at my other papers like the PySim 5G paper, so the Python simulator for 5G. But essentially what I do is I create a set of lookup tables which relates the number of cellular sites to the capacity that can be provided in an area. So it's all based on density. So it's the number of sites per square kilometer related to the amount of traffic that could be supported per square kilometer. And we use a fairly standard cellular networking dimensioning method to do this, taking into account the amount of signal that could be received, the amount of interference to calculate the signal to interference plus noise ratio to get some spectral efficiency estimate for each area. And this is a fairly standard Monte Carlo approach to estimate capacity in a local area. And this just gives you an example, therefore, that for some particular density for the different bands that are in place, and you know, this could be 700 megahertz, 3.5 gigahertz, or 26 gigahertz, that you get some specific capacity based on the density of cells, because obviously the signal drops off as you move away from the cell site. So to calculate the capacity, we obviously need the amount of spectrum that's in place. So for 4G and 5G, we estimate how much spectrum is currently being used in the different countries. So for 4G, the standard operator might have 10 megahertz bandwidth at 800 megahertz. They might have 10 megahertz bandwidth at 1800, for example. And then this is all regionally specific, of course, to the countries that we're modeling. Endowments will vary based on different countries. And also the other caveat is that this is for an average operator. And then for 5G, most countries currently are deploying using a 700 megahertz, and this is particularly true in Europe. Obviously, it's quite limited, the amount of spectrum that's available here, because it's desirable spectrum. So 3.5 is where a lot of the main urban capacity is coming from, and quite large bandwidths are able to be provided to each operator here. So 40 to 50 megahertz, for example, can be provided, and that can provide quite a significant uplift in the amount of capacity that users can access. So these are the types of spectrum portfolios that we model for each country. And we are just finishing off our engagement now with other countries that we've been working with to basically validate a lot of these input assumptions for the model. So before we can estimate how much new infrastructure we need to estimate a baseline for each of the countries. Some countries very kindly provided us with the actual data, and if they didn't, then we had to take tower count estimates. And we basically had to disaggregate the number of towers based on some understanding of the total population, the number of people with coverage, the number of towers, and the population in a certain area. And basically, I rank all of the areas based on population density and start to allocate the towers to the most dense places first. So that's the rational way which a mobile network operator would deploy. And then eventually you run out of towers to allocate, and then all the areas beneath that don't have coverage. And that matches up quite nicely with what you would see in reality from the actual coverage maps. So in the baseline, we also need to estimate the backhaul technology, which is pretty hard because we don't necessarily have statistics on the sites, and therefore we need to make some estimates here. So I take data from the GSMA based on the composition of the backhaul technology, and they provide that for Europe, Latin America, the Middle East, North Africa, North America, Northeast Asia, South and Southeast Asia, and Sub-Saharan Africa. And for each country, depending on which region it's in, I take the 2017 estimate for the backhaul. And basically, I work from the assumption that the sites in the most dense areas have the highest probability of having fiber. And then once you've allocated the 4% of sites which have fiber, the next most dense sites are likely to have copper. So this is essentially a sequential probability. And then microwave takes up the largest chunk of all of the sites. And then in the very least dense areas where we have sites, so the most remote areas, we say that they're satellites. So this is a disaggregation. It's not the specific data, but in the aggregate, our backhaul composition is the same as what's been stated by GSMA, and that provides us with some confidence that we're not introducing unnecessary uncertainty into the model. So the baseline infrastructure is hard for existing fiber, and I don't want to go into too much detail here, but essentially what I do is I take a global population layer for the number of for population density at the local level, and then I create settlements that have certain sizes and certain characteristics, and then we take existing data that we have on known fiber optic locations, and then basically we generate the least cost network design for either regional nodes or for core nodes. Okay, so I can show you some of this, again for Mexico. So this is the agglomeration layer. So I basically create a set of code which identifies all of the areas which have a population density which exceed a certain value, and therefore gives some indication of clustering. So these are settlements essentially. And then I select all the areas that say have over 20,000 people because they're the ones that you want to connect. That provides us with some understanding of where all the settlements are. I then take the existing fiber routes, so you can see them here in red. If I just turn them off and turn them on again, I'll just make this bigger. So this is all of the existing fiber in Mexico. And then for any settlement that's within 5 kilometers of this existing fiber, I assume that it has a fiber node because any rational operator would want to connect those settlements. And then for all of the other settlements that we want to connect, which are these blue dots here, which aren't currently on the fiber core network, I essentially designed the least cost network that can connect them all back into the closest fiber route. And then this local blue network can either be fiber or microwave, depending on the strategy. But it's a way for us to connect the actual settlements back into some sort of fiber network and actually extract what we think would be sensible cost estimates for doing this. And we're able to then place certain engineering constraints on the routing of this. So we know that wireless microwave links work well up to about 40 kilometers, but after 40 kilometers, you probably need to have a repeater, and therefore you can factor this into the cost equation. And we do have existing coverage data. So this looks a bit messy. Let me just remove some of this. But we have 2G, 3G, and 4G coverage data for all countries in the world, and we're able to therefore estimate which technologies are in place for the sites that are in different locations. And this is important because you need to estimate what technology is currently in place. So that's how I do the baseline core network estimation, and you end up with some maps like this for the different countries that we've operated, that we've analyzed. I mentioned just at the end there that we need to basically estimate what the technologies are in place. So whether it's 2G, 4G, 5G, and essentially most sites at the moment are 2G or 3G. And then we're either upgrading them to either 4G or 5G NSA or to some sort of fancy 5G standalone, which has all of the fancy 5G design characteristics and can provide certain use cases. So for 4G, imagine that we can deliver just a basic mobile broadband use case. But with 5G NSA, we're able to deliver enhanced mobile broadband and potentially higher capacity massive machine type communications. And then for the 5G standalone with Cloud RAN, we're able to basically enable all of these, but we also include some estimates for the number of some distance constraints, which allow us to then estimate latency. And we've worked with operators who are deploying these right now, so that they have certain rules that allow you to estimate how much latency you would get by spacing different nodes at different distances, and we've used those within the estimation process, so that we can basically build this virtualized network which has edge compute. And how do we do that? Well, for each site in the Cloud RAN, which doesn't have its own compute on site, it has to have a fiber front haul link to a local cloud node where you have some commercial off-the-shelf processing facilities, and then you essentially need to link that back through a regional cloud link to some regional cloud node, and then back to a central cloud node. And we take that into account in the calculations that we do in order to cater for the geographic characteristics of trying to provide lower latency use cases. Okay, so we did a survey to estimate the costs for different assets. I'm not going to go into too much detail here other than to say that we did it and we got mean costs. Academics aren't very good at estimating costs, and it's commercially sensitive for many operators. So it's quite hard to do this without actually knowing the real implications. And we're able to allocate those costs based on the different types of network architectures that we test. Spectrum prices are really hard to do, but essentially for each of the 6 clusters, we analyzed past spectrum prices, and then we made assumptions about the cost of the spectrum in each geography based on the type of spectrum, and that's essentially some sort of dollar cost per megahertz per population member. We were able to get the total cost by adding together the network, the spectrum, the taxation, the profit, and that's essentially a composition of what the network cost is: the RAN, the backhaul, the core, and any subsidy. The spectrum cost is basically the frequency that you have, the bandwidth, multiplied by that dollar cost that we had per megahertz per member of the population. And they're fairly standard, fairly basic calculations to estimate these analytics. Okay, so results. So as I mentioned, we are finalizing this work right now, so the work is still ongoing. But essentially what we've been trying to do is to present the results in terms of the cumulative cost for serving up to 100% of the population, essentially. Although that may be highly ambitious, the aim is to at least provide some analytics to understand what that might cost. And we have the cumulative revenue for the demand side in the red curve here, and then we have the cumulative costs for different technologies based on these other options. In essence, just kind of highlighting the findings so far. 5G microwave looks like one of the most sensible options because it has a higher spectral efficiency, and microwave is generally cheaper to deploy. We find that as you start to increase the capacity for users, it gets very expensive. And while 5G standalone may be very good at moving those large amounts of data, it's just often way too expensive to deploy in many of the countries that we're looking at here, because there's so much fiber and other compute that needs to be deployed. Maybe in central urban locations, it might look reasonably sensible. So in terms of infrastructure sharing, we test baseline, and we're getting somewhere between 10 to 40% cost saving, depending on whether you're deploying a passive site sharing approach or an active approach where you're sharing electronic components. And out of the analytics that we are producing, we're able to also look at the cost composition and break these cost compositions down in terms of how much is being spent on the RAN, how much is being spent on things like taxation, and essentially where the state may need to pick up the bill if there isn't enough capital available to deploy to unprofitable areas, essentially, unviable areas. Spectrum costs are a huge issue, and they have a really large influence on the viability of the rollout of 5G. So high spectrum costs can make a 5G rollout completely unviable, whereas lowering spectrum costs by, say, 50% have the opportunity in some circumstances to make the entire rollout completely viable. So that's almost 100% 5G coverage. And this is a really important finding, and it will be one of the key messages that we report in the output that's going to come in the next couple of months. And taxation also has a large impact because of the way that we modeled it here, which is more of a corporation tax rate. It had less of an impact than the spectrum costs, but obviously they are both effectively different types of taxes. So I appreciate that I'm out of time, so I'm not going to present this next section to you on the software that we've developed recently. I'm just going to finish there. And thank you all very much for your time, and I'm happy to take any questions if we have any time left. Thank you. So I'll start with one of the questions that's been raised here. So for less developed countries that mostly use 2G or 3G currently, do you think that it would be more profitable in the long term to develop straight to 5G standalone or develop 4G LTE infrastructure first? Which option will be more likely? Okay, that's a great question. I think that 5G standalone is just not viable at all in those low-income and middle-income countries. And that's because you basically need to do proper 5G standalone, to deliver all of the low latency use cases, you need fiber. And the fiber cost is just astronomical. You have to basically do as much with microwave or wireless backhaul as you can in many of those countries and those locations. Because 5G NSA has a more spectrally efficient radio interface, it was definitely potentially cheaper to deploy 5G non-standalone in certain circumstances than deploy 4G. And I think that that's an important finding. You know, you're able to reduce the number of sites that you use. So I think that we will thoroughly articulate this within the final report that comes out in 2 months. But that's our current thinking, that in certain circumstances, leapfrogging to 5G NSA is potentially a sensible option. So I'm happy to take more questions. I don't know how much longer we have. I know I was meant to talk until 1:45. So if someone wants to give us some direction, that would be great. Do we have 10 more minutes for questions, or is this it? Oh, 5 minutes, okay. I'm happy to take any more questions that you might have. Either just speak out now or write them in the Zoom group chat. Well, if there aren't any more questions, I'm happy to share the presentation with you all, by the way. Oh, how do I see the difference in continents? Well, the problem is that it's quite country specific. And a lot of the problems in getting to almost total coverage depend very much on country specific factors like geographical area and population density. So the fact that we had Albania in there which is relatively small geographically. And yet then we had Pakistan, which has this really, really high population density. And then we have Mexico and Peru also, which have very large geographical areas. Makes it quite hard to generalize across the different continents. I think, that there's a lot of focus right now on particularly Latin America, as there's scope there to roll out infrastructure, and generally incomes are high enough for people to pay small amounts per month. It's quite challenging as you get to rural areas in sub-Saharan Africa. It's because for a variety of reasons, ARPUs are incredibly low. And even if you increase the penetration, if people are only topping up 20 cents per month, actually, even if you push up the penetration to like 80%, it doesn't generate that much revenue. And, if you can't make the infrastructure pay, it's quite hard to build it. So that's something that I definitely see within the modeling. So what are the main issues for developing countries for early deployment of 5G networks other than income? Spectrum and taxation spectrum prices are high relative to the market potential of different places. So on face value, the spectrum prices might be higher in the USA or in European countries compared to Senegal or Malawi. But then when you look at it in terms of the amount that people are actually able to pay, the spectrum prices are very high. What we've been trying to emphasize in the report is that if you use all of the policy options that we put forward, so if you encourage infrastructure sharing, particularly in unviable locations, if you lower spectrum fees by about 50%, and if you cut taxes by about 50% of what they are currently, you can get, in most circumstances, to about 90% coverage, which is huge. I mean, the fact that most of these coverage issues can be solved through political economy decisions is really important. That's a really nice finding. So I think that that's something which will be key going ahead. I think my hesitation about saying that countries should move directly to like a 5G standalone approach is that we just have so many unproven use cases there so far. I mean, that's the feeling that I'm getting, and that lots of operators are deploying 5G non-standalone to try to sell enhanced mobile broadband to people. And that's fine, I think, in OECD countries where people can take a bit of the risk, but capital can be so short, in such short supply in some of these low-income countries, that it seems an incredibly risky option to me that you would invest, what is up to 1 to 4% of GDP in deploying 5G standalone. So really what I think is key is also trying to get the fiber density up in certain locations, because I feel a bit like fiber is a win-win. You will always use it. It's always great to have fiber nearby, and that will help the further evolution of broadband access in the future, such as with 6G. I appreciate there's one more question, but I've been told that we have to cut off after the last one, I'm afraid. So email me if you want me to try and answer that last one. But thank you very much, everybody, and I hope you have a nice day.
Thank you, Edward Oughton from Oxford University.
Next up will be Henrik Lehmann Christiansen from Technical University of Denmark.